Hello everyone, I'm Vivek. So Habiba just gave a great overview of why your extended reality device knows exactly where you are. And now I'm going to be telling you why it knows exactly who you are. So I'm going to be talking about unique identification of over 50,000 users in virtual reality based on head and hand motion data. So the previous speakers have already given a great overview of virtual reality, but I actually want to step back for a second and talk about the origins of this field of motion-based identification and inference, which actually go back to well before commercial-grade VR, at least to the 1970s with this pretty famous paper from Cutting and Kozlowski. What these two authors did is they took a bunch of participants into a lab and had them walk around, just act natural. But they attached these little points of light that are called markers to various points on these participants' bodies. And then this is before any kind of sophisticated computer graphics. So they literally took a camera feed of these participants, plug it into a CRT monitor, and just crank up the contrast level until the silhouette disappears, and all you can see are these points of light moving around. And so this is what it actually looked like in that study. And they showed these images of these lights moving around, or video feeds, to some friends of these participants, and then asked them, hey, just based on these points of light moving around, can you name exactly who you're looking at? And it turns out that people can do this with moderate but statistically significant accuracy. This is something that we never really practice how to do, but strangely just have an innate ability to recognize our friends based on their motion patterns. The reason this should be interesting to us today is if we look at virtual reality devices, what are they typically capturing? Well, typically you have at least a headset on your head, you have two controllers or some kind of hand tracking, and these are just points that are being tracked moving around in 3D space. And if you're using sort of a metaverse or multi-user VR experience, then this location motion data is not only being sent to the application to render frames for you, but is also being forwarded to a server and then on to other users around the world. And the reason that this is striking is because it should look shockingly similar to the exact same type of data that we've known for almost 50 years is uniquely identifiable and reveals information about users. And so I'm definitely not the first one to make this observation. So there have been a number of studies on identification in VR. The most famous one until now is the Miller, from Mark Roman Miller out of Stanford, where he had over 500 users in VR that could be uniquely identified with up to 95% accuracy based just on their head and hand motion patterns. So this shows that there's really something there. That just by putting on your VR device and moving your head and hands naturally, you're actually revealing a signal that is fairly unique to you. Only slight problem with this existing work is that you also are just revealing static measurements about yourself. So for example, the Y position of your headset just measures your height. And it turns out that these static measurements like height and wingspan are enough to identify about 4,000 users uniquely on their own. So by contrast, and not to bury the lead here, so the result I'm going to be talking about today is over here with 55,000 plus users still uniquely identified with close to 95% accuracy based on head and hand motion data. So now we're getting well beyond what like your height and wingspan and so on can identify you with. And the way we did this is obviously not with bringing 55,000 people into our lab at Berkeley. This would have been totally infeasible. So instead, we used a VR game called Beat Saber, which is one of the most popular VR applications of all time. And it's this rhythm game where you kind of cut blocks in time to music. And the interesting thing about this game, Beat Saber, is that it has turned into quite a competitive scene. So we have a esports team at Berkeley who plays this, but there are teams all around the world who play competitively. And so there are all these leaderboard services that have popped up where people like to upload recordings of themselves playing Beat Saber to prove that they made a new high score on a certain level. And when they do that, they actually attach motion capture data of themselves, their head and hand motion playing the level. And this is sort of their proof that this was a real human-generated score. And so we were able to get access to this data set from BeatLeader, which is one of the largest such leaderboard services, which contains these head and hand motion capture recordings from over 55,000 users. Actually, today it's more than 100,000 users. And these are users all around the world, 40 plus countries, using 20 plus different types of VR devices. And together, we got about 4 terabytes of data with almost 3 million recordings of VR users. So there's a much more diverse representative data set than you can get from just a laboratory study. And what we did with this data is we actually plugged it in to a classical machine learning model called LightGBM. It's a type of gradient boosting model. And LightGBM expects tabular data, so we first have to convert this time series data into some tabular features that the model can understand. In our case, we just did this by taking some certain summary statistics across each of the track dimensions. And this is the same approach that the prior work has used, including the Miller work. It happens to work better empirically than some of the deep learning attempts. And so then you get this LightGBM classical model that we train as a multi-class classification model with 55,000 classes, 1 for every user. And we just try to classify the motion data into one of those classes. And so there's a few other tricks that we use that I won't be able to dive into right now. But we add some contextual information to help the model understand what's happening inside the game. And we also use a hierarchical approach that is shown here. And the bottom line is that with all of the models applied sequentially, we have about 94% accuracy of identifying the correct user based on their head and hand motion patterns from a completely separate session than when they were enrolled into the system. So an average of 2 weeks later from when the model learned their motion, their new motion can be used to identify them. And actually, the curve looks something like this. So imagine you're putting on your VR headset, right? So within 2 seconds, I have a 50% chance of picking you exactly right out of a crowd of 55,000 options. If you keep it on for 10 seconds, I'm up to a 75% chance of picking the right identity. And then all the way up to about less than 2 minutes, 100 seconds, we are reaching close to 95% accuracy of picking exactly the correct person. And for the first time, we've shown that this result actually comes mostly from your movement patterns, not just your static measurements. So static features are still the most important individual features, like height and wingspan. But in aggregate, your motion features account for almost 75% of the entropy gained by this model for identification. And then those context clues that I mentioned earlier give another 3% slight boost to the information gained. So just to put in context what this result means for the field of VR, we're now getting to the point where your head and hand motion data, as observed by a virtual reality device, is sort of comparable to a lot of classical biometrics like fingerprints, iris scans, facial scans. The actual numbers on these biometrics vary a lot depending on what sensor you're using and so on. But we're now in the same ballpark, right? We are now talking, you put on a VR device, you use it naturally, you are revealing something like a fingerprint scan worth of identifiability to the device. And that's important because recall when I opened this talk, I mentioned that in a metaverse setting, you're sharing this motion data not just with the application, but actually with every other user in the metaverse with you, right? So that they can render your avatar on their display. So the way this works right now is sort of the full raw fidelity data going to all the users. It's like equivalent to if you were to log into a conventional social network and you have to upload a picture of your fingerprints, not only to the network, but to every other user on the social network gets to see your fingerprints, right? This is sort of the equivalent of how current metaverse platforms work. And so, with Apple entering this field, it's going to be an increasingly important area of research, I think. And this really demonstrates the need for privacy-preserving technologies for virtual reality. So just want to emphasize everyone in the room here that this is an increasingly important problem to solve. So with that, thank you, and happy to take any questions.